I can't see most of you, so I will be probably a little less nervous. Good morning, I'm Harini Sridharan. I'm a postdoctoral researcher at Oak Ridge National Lab. Today, I will be talking about our efforts in developing a scalable computational framework for monitoring critical infrastructures using high-resolution imagery. Critical infrastructures are vital elements for emergency planning and preparedness. As part of our efforts to support the Homeland Security Infrastructure Program, we have been actively involved in collecting data on critical infrastructures. Since satellite imagery can provide cost-effective and efficient solutions to this process, we have been directing some of our efforts in developing automated image-driven solutions. An automated framework typically involves an image passing through a big black box, and in the end, the expectation is a map or database containing information about these infrastructures. Now, when designing these boxes, there are two primary challenges to be faced. The first is the very high within class variation within a given semantic class. The image on the left here shows samples from mobile home parks collected from various cities across the country. Note how different they are in their arrangement and appearance, and note how similar they can be to a sample collected from a warehouse containing just trailer homes or 18-wheelers. The second challenge is that the solution that we developed should be applicable to any geographical area using any type of high-resolution imagery at any given point in time. So what we needed was a unique scene representation that can effectively and efficiently distinguish between different semantic categories and is also invariant to any type of changes. We experimented a lot, and we came up with a line-based scene representation that can be a great solution to these identified challenges. Different infrastructure facilities have unique physical object attributes. For instance, a mobile home park scene has mobile homes oriented in a specified spatial pattern, and a shopping complex scene just has one large building. Straight lines detected from the imagery can closely relate to the physical geometry and the spatial arrangement of the local structures present in the scene. A key advantage of this type of line representation is that any type of changes in imagery, like scaling, rotation, or change in appearance, that does not really change the relative relationship of the lines. We therefore decided to analyze the local line patterns of the scene and incorporate this idea into an automated framework. So, I'm waiting for the next slide. Okay. So we developed a two-level hierarchical framework, and this flowchart shows the basic idea of the framework. We divide the image into patches and pass it through the first level. At this stage, we distinguish or segment the images between segment and non-segmented region using basically textual features. And then we eliminate all the irrelevant patches such as vegetation, water, and barren lands. And those patches that do survive this stage go on to the next level. At this level, we detect the lines, analyze the local patterns, and have developed an SVM model that will identify or detect a specified critical infrastructure. Now, this entire framework is supervised, and training is done by using pre-collected samples. But once it's trained and tested, it can run automatically. So we have tested or applied this framework for detecting mobile home parks. We have collected about 7,415 samples from 11 states, and we have trained a model. We performed a 5-fold cross-validation. You can see how the different samples collected from various geographical areas are very different. So the basic idea of the framework is to generalize how a mobile home park looks and apply this model to any imagery from any part of the country and do a detection. So if you look at the accuracy numbers, we can see that a high degree of accuracy has been achieved using this framework. And we also found that this framework can be applied robustly, consistently across various geographical areas to any type of high-resolution imagery. A typical output of this framework looks like this. This is a region from Rhode Island. The blue markers there show the settlements from level 1 detection, and the yellow markers are the detected mobile home parks from stage 2. A closer view is also shown. We have a GPU implementation that processes detection at the rate of 28 square kilometers per minute. So we are doing a national level production, and we have completed 30 states so far. The outputs from 11 states are shown there. And we are focusing on extending this framework to other type of critical infrastructures like hospitals and schools, etc. So thank you, and I'll be happy to answer any questions.